Pipe is a high-performance parallel computer specifically designed for processing images at real-time frame rates. It is a modular system with 1 to 8 parallel processing stages. Pipe is an integrated hardware-software system that allows users to program most all low-level vision functions as easy software tasks with the same hardware configuration. Unless otherwise mentioned, all applications that you will see on this tape were run on a 3-stage pipe with an ISMAP along with an AT386 computer. Pattern matching algorithm running on Pipe and the 386 computer matches edge directions and allows translation, rotation, and scale invariant recognition. Here it has been trained to recognize the front and back of this video cassette. This has many applications in sorting and inspecting objects that are not well fixtured or are irregular. The centroid of moving objects can be found by taking thresholds of image differences and computing the first moments and areas. The red crosshair shows the centroid. This has many uses in tracking objects. The centroid algorithm and a neural network were used by Dr. Alan Waxman and his students at Boston University to guide a small robot arm to track an object on a conveyor belt. They have used the same algorithms to control 2-camera stereo vergence and tracking. These algorithms were also used to enable a mobile robot to follow a bright light. These applications from BU used an 8-stage pipe, an ISMAP, and a Sun 3 computer. A stored known good edge image of a product is continuously correlated against new images flowing in. The result is a single number that is 0 if they are identical and non-zero if there's a flaw. Here the flaws are simulated with small pieces of paper. The log polar transform is a good example of an image remapping function. At Lockheed in Sunnyvale, California, Pipe's remapping capability has been used to create real-time terrain mappings. Here, a spot satellite image of the coast at Bath, Maine has been registered and draped over topographical elevation data. By using NOAA underwater depth soundings, a composite view of the coast above and below sea level can be seen. This application uses a 3-stage pipe and a Sun 3 computer. Nonlinear remappings could be used to reduce the bandwidth requirements for controlling teleoperated vehicles, or RPVs. Here the image is shown at high resolution only where the operator is looking and low resolution elsewhere. The position of the high resolution area can be controlled by an eye tracker worn by the operator. Pipe's Boolean morphology capability allows connectivity preserving thinning. This has many uses in industrial and printed circuit inspection. Connected component analysis has many uses such as multiple object measurement, region analysis, and multiple object tracking. Here, each area larger than 19 pixels has its enclosing box, centroid, angle of orientation, and area displayed. This connected components algorithm is running in software on the 386 computer. This long telephoto shot of the space shuttle on final approach is bouncing all around. Here is the same shuttle sequence dynamically centered by pipe. This allows temporal image enhancement to be performed, reducing noise. The original image here is a white bar on a black background. By using Gaussian curvature, the four corners of the bar are found and marked with white dots on the red background. Here, those four corners are read out to the 386 computer and matched to a rectangle model that does not allow the lines to cross. Three-dimensional model matching has been performed by Dr. Chuck Dyer and his students at the University of Wisconsin using an 8-stage pipe and a sequent computer. A model of the object and the camera geometry are kept in the sequent, and these are matched to the edges found by pipe. This has many uses where a model of the object is already known, like a CAD database. Pipe is ideally suited for performing motion flow computations. Here, the normal edge velocity is represented in grayscale. The faster the edge motion, the brighter the edge. Here, the normal edge flow direction is represented in color. Up is red, down is cyan, right is purple, and left is yellow. Diagonal directions are the in-between colors. Edge detectors are very simple on pipe. This shows thresholded edge gradient directions from a Sobel operator. Edge angle is represented in color. This is a composite of two edge detectors. A thresholded Sobel magnitude image is logically ANDed with the zero crossings of a Laplacian image. The Hough transform is good for showing how broken lines might be connected together. The thresholded edge image is shown in the lower left corner and the transform is shown across the top. The two bright white areas in the transformed image correspond to the two lines. Here is a view of the 386 computer screen showing the families of lines that correspond to the two bright white areas in the Hough transform. Pipe is programmed with a menu-driven graphical software system called ASPipe. For this quick tour, the programming of a simple Sobel magnitude operator will be demonstrated. First, a loop needs to be made. Here we see a two-dimensional chart with pipe stages arranged horizontally and time cycles in frame times arranged vertically. Because the Sobel is so simple, it will only use one cycle and one processor. Now we move the cursor down into the chart and start programming. We will follow the signal flow. Starting with the video stage, we click on it and a chart of the video input is brought up. Program the camera source and the A to D. Escape out and go into the input stage. Program the buffer mode and frame buffer A. Escape out and program the other half of the input stage from the buffer on out. Program the buffer mode, frame buffer A, and the forward path to the first processor. Escape out. Notice the forward paths are now shown. Go to processor 1, move to the forward lookup table, select a table from the directory called Unity. Set ALU A to always put out a 0. Set ALU B to add ALU A to the output of the forward lookup table. Program the buffer mode and program frame buffer A to use ALU B as its source. Escape out and go to the post buffer half of the processor. Program the buffer mode again. And frame buffer A. Set the source for the neighborhood operators to be buffer A. Select the Unity lookup table here too. Set neighborhood operator A to use the mask for the X gradient. Set the mode to 3x3. Set neighborhood operator B to use the mask for the Y gradient. Go to the two-valued function, the TVF. Program its A operand to be the neighborhood operator A, the X gradient, and its B operand to be the neighborhood operator B, the Y gradient. Set its mode and select the two-valued lookup table for computing the magnitude. The TVF output is selected onto video bus A, where it is picked up by the video stage's output for display. Here we program all three lookup tables with Unity sourced from video bus A. This will give a monochrome display of the magnitude. If we had used an arctangent table in the TVF and three color mapping tables here, the output would be the color display of edge angle as was seen earlier in this tape. Escape out. Then the loop is saved. Then compiled into microcode and loaded into pipe to run. The lookup tables and neighborhood operator masks are created with LutGen. Arithmetic NOP is used to create the masks for the arithmetic neighborhood operators. Here, the mask for creating the X gradient is entered. And then it is saved out as a file. Boolean NOP is used for the Boolean neighborhood operators, and equation is used to create single and two-valued lookup tables. Here we will look at the two-value lookup table for the Sobel magnitude operator. The blue area at the bottom is used for entering the equations. Here the equation is the square root of a squared plus b squared times 1.414. We can graph its transfer function out as an isometric plot with a horizontal, b diagonal, and the output vertical. You've just seen a selection of applications demonstrating the incredible versatility of the pipe system. If you have a particular requirement, call us. We'd like to talk with you about your application. We can send you written or videotaped materials that go into greater depth on these and other applications of the pipe system.